the introduction and the invitation to present. So as Dave mentioned, we're looking at risk and resilience assessment of bridge
Alright.
networks um, using these simulated ground motion. So that's sort of the long-term vision, right? So to look at the bridge network in the Bay Area and look specifically at functional recovery performance. Now, we haven't quite gotten there yet. We just started working with the record. So what I'm going to show today is primarily a pilot study where we looked at a couple of a single bridge type placed at a couple of different locations, and basically focusing mostly on bridge specific performance. Again, with the long term vision to extend this to look at the entire network. So as I mentioned earlier, what we're interested in is when we say risk and resilience, our performance metric is the post-earthquake functional recovery of these bridges. So we recently published a paper here that's going to be released in Spectra. I'm going to quickly go over the framework so you can get a sense for how we're assessing performance. But again, you can get more of that information from that paper. So part of the motivation is, Caltrans has been continuously advancing its seismic design objectives. So initially, it was just based on life safety, where you had to evaluate your bridge for a design-based earthquake. That was a 975 return period. And then in version 2.2, that was extended where you had to also look at a functional evaluation earthquake based on a 225-year return period. Um, and so part of what we're trying to do here is try to get a little bit more specific in terms of how you can do functional recovery evaluation for bridges, and have sort of an explicit quantitative framework that you can use for that assessment. Now, as I'm sure a lot of you know, there's been a lot of work done on functional recovery for buildings. It's sort of in the national, it's part of the national dialogue, particularly within the earthquake engineering community. There are folks involved in the building code, trying to advance the building code. But there are a lot of differences when it comes to functional recovery for bridges versus buildings. So, for example, the ownership is very different, right? So buildings are typically owned by homeowners, businesses, and the repair efforts tend to be very centralized. Yeah, so like I was saying, there are a lot of differences when it comes to thinking about functional recovery for buildings versus bridges. So I talked about the differences in ownership. Um, the way that we define the different recovery states for buildings versus bridges is different. So for buildings, we focus on reoccupancy, functional recovery, full recovery. Whereas for bridges, we think about, what are the ways that the bridge access can be limited. So you can have lane closures, weight limit, speed limit, things like that. And then the financing structure is also very different. So building owners rely on having cash on hands, private loans, insurance, whereas for bridge networks, there's a reliance on federal and state funds and just maintenance funds. So when we talk about functional recovery, what we mean is that we have a model that probabilistically quantifies how the bridge progresses through different states of functionality while accounting for these different types of disruptions that I just mentioned earlier. So this is a high level overview of the framework. So the first part of it, the first two steps, the hazard and damage analysis, those are sort of typical, sort of unchanged relative to the PDE framework that we all know and love. It's this second portion here that we spent a lot of time on things like how do you define the functionality states, thinking about impeding factors, repair activities, and coming up with the recovery time. And getting sort of a reasonably well representative structure for all of this was not an easy task. We spent a lot of time in conversation with folks from Caltrans and local California engineers and contractors to get a better sense of one, how these different sort of organizational factors are sort of um, how they're architected, as well as data that are needed, as particularly temporal or time-based parameters, how those are used within the post-earthquake environment. Um, just quickly, we for the damage analysis, the framework accommodates a couple different approaches to simulate to assessing damage. You can do what we call an IM based, where you just look at where you just simulate the spectral intensity at the site of interest, and then based on based on fragilities defined for the bridge component that link the shaking intensity to damage, we can use those and sample the damage. Or you can do what we call an EDP-based approach, where you start with site-specific ground motions, you do response history analyses, and then you have a component demand model that you probabilistically compare with a capacity model, and you use those to simulate damage. I mentioned before that we spent some time getting information from Caltrans field engineers and officers, California bridge engineers, as well as contractors. We had 5 different rounds of interviews, and that allowed us to collect different types of information and data, like, information about bridge closure and reopening decisions. What are the different impeding factors that we have to consider, and how they're sequenced, and what are their durations? Similarly, for the component repairs, how are they sequenced? And thinking about trying to be realistic in terms of worker allocations. So I mentioned earlier, for the functionality state definitions, the disruption of functionality is based on these three inhibitions, if you will. So either complete link closure, partial link closure, or reduction in the weight limit. And so based on that, we have 7 discrete functionality states. 4 of them are associated with the initial response, meaning right after the event. You have 4 functionality states that can happen either right after the event or during the reopening. And then 3 of them, 4, 5, and 6, are only applicable to the reopening phase. I mentioned before, one of the things we had to spend a lot of time thinking about was the impeding factors. So these are activities that need to be carried out before you can even start the repairs. And as we know, based on experience with buildings, these can take quite a bit of time, and depending on the amount of damage, the duration can even exceed the repair time. So it's important that we consider these things. In addition to considering these impeding factors, it's important to understand sort of the workflow after an earthquake, and how that affects the sequencing of the impeding factors. So right after an earthquake, there's typically a visual inspection of a bridge. And then based on that visual inspection, there's a determination of whether an in-depth inspection is needed. So these are cases where maybe based on the visual inspection, it's not obvious whether or not the bridge should be partially or fully closed. And then based on that in-depth inspection, you finalize the bridge closure decision. And then there's a sequence of activities that need to happen. So the design, acquiring a contractor, permitting, and the sequence of these depend on whether or not an emergency protocol is triggered. So basically what the emergency protocol does is it fast tracks the selection of the contractor. So that's done in parallel with the design, and that's all done. A lot of that is done. All of that is sort of predetermined. There's predetermined protocol for how to sequence a lot of this based on whether or not there's an emergency protocol. So we can consider the case with or without that emergency protocol. Okay, so we're doing component level assessments, right? So we're simulating damage to individual components, and these are the components that we're considering here. And for the abutment, we can zero in and look at the different types of components that are associated with the abutment. And so in addition to understanding what the components are, what's their vulnerability, we need to understand how the repairs of these components are sequenced. So what I'm showing here is for 2 different types of bridges. The row that's at the top is for a diaphragm type bridge, and the row at the bottom is for an abutment type bridge, and it shows for those two different types of bridges how the sequencing of the different types of components must be carried out. Okay, so I mentioned before that what we've done to date is a pilot study where we looked at a single bridge, an identical bridge. We have an OpenSeas model for it, and we placed that bridge at two different sites based on the simulated ground motion field. So one site was about a kilometer away from, had a bore joint a distance of about 1 kilometer, and the other one about 24 kilometer. And so the bridge we considered, it was an what Caltrans classifies as an era tree bridge, meaning it was designed and constructed after 1971. It has two spans, three columns per span, and it's a seat type abutment bridge. Um, and so we implemented the EDP based approach to assess the performance, meaning we started with an OpenSeas model. We selected we took the 50 realizations of ground motions at each site, and we did response history analyses of those ground motions. This is just a quick overview of the detailed nonlinear structural model that we used. I'm not going to go into too much details of that, but we're modeling in detail a lot of the components, the response of a lot of the components that we need to simulate the damage for. So as I mentioned, we have these two sites, one that's about a kilometer, a bore joint, a distance of about 1 kilometer. The other is about 24 kilometers. This slide shows the geomean spectra for those two sets of ground motions. If you look at the vertical axis, they're scaled differently just because of the differences in intensity. So for the near field set, the peak there is at 2.5, and for the far field set, it's at 0.5. So that's just to give you some context into the differences in the shaking intensities associated with the two sets of ground motions. And the vertical black line, so the bridge itself had a period, a first mode period of about half a second. So that gives you a sense of where sort of the modal response is relative to the spectral shape of those ground motions. Okay, so we took those ground motions. We have an OpenSeas models. We ran those ground motions through an OpenSeas model. And what we get is a set of response demands for different types of components. Now, earlier I showed, I don't know, about a dozen or so components that we're considering, that we're explicitly modeling the response and damage for. Here I'm just showing a couple of them for illustrative purposes. And what I'm showing here is the probability density function for two types of components. On the left, it's the column curvature ductility response. And on the right, it's the deck unseating displacement. So the one on the right is basically the demand parameter that's used for simulating the unseating of the deck. And these are the two, what we call the two primary components, meaning these are sort of considered the safety critical components. So once we have those responses, we can probabilistically combine the demands with the capacity and simulate component level damage. And so what we're showing here is the empirical distribution of damage for the columns as well as the deck unseating damage state. And you can see the distribution of damage, the empirical distribution for the near field ground motions is much more skewed to the right, more skewed towards heavier damage. And for the far field, it's much more skewed towards having either no damage or slight damage. And then from these damage states, we can get the distribution of the functional state of the bridge. The label here is incorrect. So this is actually the functioning state of the bridge. So it's the empirical probability distribution of the functioning state. And again, these are the initial response states. And as you can see, for the bridge placed at the far field site, um, it's governed by the functionality state one, which basically means that the bridge is fully functional, and then there also is some probability associated with functional state two. Whereas for the near field, it's much more skewed towards FS3 and FS7, where FS7 is basically complete closure, and FS3 is some type of partial closure of the bridge. Yeah, these are just the definitions of these different functionality states. So we can also look at results in terms of the functional recovery. So here, what I'm showing, this particular plot shows the complement of the cumulative distribution function for the repair time. And again, you can see here that for a given repair time, the near field ground motions have a much higher probability of exceedance. We can also look at the functional recovery time. Again, for the near field ground motion, for a given functional recovery time, there's a much higher probability of exceedance. But you can also see if you compare the repair time for the far field, that goes up to about 20 days before the probability of exceedance gets to zero. However, when we include the impeding factors, right, that's the difference between the repair time and the functional recovery time, is the inclusion of the impeding factors. You see that you can have non-zero exceedance probabilities all the way up to about 250 days. The other thing we did is we looked at the implication of the emergency protocol. So we looked at the near field site, the functional recovery, the CCDF of the functional recovery for the near field site with and without the emergency protocol. And remember, I said part of what the emergency protocol does is that it fast tracks a lot of the impeding factors, a lot of the activities that need to be completed prior to starting the repairs. Those are fast tracked. So you can see the effect of that here, where you have a much lower probability of exceedance for a given functional recovery time. So again, the next steps is to look at the entire bridge network, where we're going to be looking at the entire ground motion field. We obviously have to do some inventory capture and group classification to get to define the bridge network. And then we're going to look at multi-fidelity structural response and damage assessment. By multi-fidelity, I just mean in some cases we'll do explicit response history analyses, and in some cases we'll just use fragility curves that link the shaking intensity to damage. And we're going to be doing high resolution functional recovery assessment, meaning we're going to be doing this for each bridge within the network. And then we're going to combine those to get some type of network scale functional recovery performance metric. So again, the long-term goal here is to look at the functional recovery performance of the bridge network using these simulated ground motions. But for today, I just talked about a pilot study we did on bridge-specific functional recovery-based performance. And we considered the same bridge placed at near field and far field sites, and we highlighted the effect of differences in the ground motions on response demands, damage, and functional recovery for the different sites.
Hypothetical bridge. Is the bridge that you described that you were using as a sample near Fremont, is that a real bridge or a hypothetical bridge? If it's real, which one is it?
Yeah, it's a good question. So if I can repeat the question just to make sure I heard it, is whether or not the bridge is a real bridge or a hypothetical bridge. So basically, what we're going to be doing for this risk assessment is we're going to be creating these different classes of bridges, and these classes are based on the design era, the type of whether it's a diaphragm or a seat type bridge, and the number of spans and so forth. So this bridge that we use today is a bridge that's in one of those classes. So the short answer to your question is that it's a hypothetical bridge. But again, the idea is that eventually we're going to match the actual bridges in the network to our set of bridge classes based on those different characteristics.
Any other questions? Okay. Oh, one more. Burton.
Okay, I was wondering if there are any criteria to select which scenario among the many scenarios from numerical simulations. So is there any criterion related to probability, frequency of occurrence, something like that?
Yeah, that's a good question. And we're doing the same thing, meaning this type of network analysis for the Los Angeles network. We're doing that for using actual recorded ground motions, and I'll be talking a little bit about that tomorrow, and I'll sort of answer your question in a more in-depth way. But the short answer is that we do what's called a stochastic event set based hazard characterization. So we start by considering all of the events that can affect the region, and then we do an event subset selection where the goal is to have the assessment based on the subset of events to match that of the entire stochastic event set. And there's different ways to do that. We're utilizing an approach that was developed by Scott Brandenburg and others here at UCLA. And again, I'll be talking about that more tomorrow at the peer annual meeting.